All right, so let's look at this Gauss's law problem, which is incredibly illuminating. So we have two conducting hollow metal shells with a point charge that is placed at the center of the inner shell, which is little plus q, plus little q. The inner shell is neutral, meaning the inner shell has no charge, while the outer shell has overall charge plus capital Q. We want to calculate the electric field in space everywhere around this. Since we're dealing with a sphere, of course, we can use Gauss's law. So let's look at this figure. So we have the inner shell. See that the inner shell has two radii. That means it has an inner radius and an outer radius. The inner radius is A, the outer radius is B. The inner radius means it has inner thickness, the distance from the center to the inner wall, and the outer radius means it's the outer thickness, which is the radii is B. The outermost shell, that is having radius C, has no thickness at all. So it doesn't have two walls, it only has one wall. Right? And at the center of all this spherical configuration, we have this point charge that is plus Q. Don't confuse a point charge plus little q with the outermost shell having charge plus capital Q. They're two different charges. All right. So now let's calculate the electric field in space everywhere around this, and we will definitely be using Gauss's law because it's so much more easier to do with a symmetrical system like this. So the first interesting region that we will look at is we would look at the inner portion of the innermost shell. So let's just express Gauss's law if you don't remember. Gauss's law tells me that the integral, like the electric flux is defined as the integral of E dot dA through a closed surface is equal to the charge inside or enclosed by that closed surface over epsilon zero, which is a fundamental constant. dA, if you don't recall, dA is just the area element if you cut out the sphere into infinitesimally small pieces. And dA is always, for a closed surface, it's always a vector that points out of that closed surface. So it turns out that dA is in the radial direction for a sphere. So now we look at the inner region of the inner shell. So it's good to note that the inner portion is hollow. All right. And so we draw a Gaussian surface to apply Gauss's law. The Gaussian surface now resides inside the inner shell. That is, the radius of the Gaussian surface is smaller than the inner radius A. All right, so if we apply Gauss's law, we are going to consider this radius. All right, R is less than A. So let's do it. For R is less than A, then Gauss's law, we can write it out as the integral of E dot dA, which is just E dA cosine of the angle between them. Cosine of the angle between them. Now, let's see what the angle becomes using a different color. The angle is between the electric field vector and the area vector. Now, the electric field for this positive charge that is inside my Gaussian surface is radially outward. For any point charge, it's going to be, if for positive charge, the electric field is going to be like emitted outwards of that positive charge. And the area vector, as I discussed before, is just a vector that is perpendicular to your Gaussian surface. And it turns out the area vector for a closed surface is always pointed outward along the radii. So both the E and the area vector are parallel to one another. So think about what the angle is going to be for a second. The angle between dA and E would be 0. So then on the right hand side, we have the Q enclosed by the epsilon 0 term for Gauss's law. So what is the Q enclosed? That is the charge that is inside my defined Gaussian surface. I can clearly see that is just little q, that is the point charge that is inside my defined Gaussian surface over epsilon 0. As simple as that. There's no other charges, just little q. Cosine 0 is 1, and the electric field at the surface of my Gaussian surface is constant because it's from the radius is the same to all parts of the surface. So you can bring it outside the integral. And so we can write this as q over epsilon 0. And the integral of dA is just the total area of that surface. Now the total surface is just a sphere. The area of a sphere is then just 4 pi r squared. Okay? So then you're solving for E. Remember, E is the unknown here. So you're solving for the electric field. You don't know any formula for the electric field. Don't assume Coulomb's law. So E is the unknown that you're solving for. So you divide both sides by 4 pi r squared, you get your electric field. So the electric field becomes E equals, let me get that right here. Electric field is equal to Q over 4 pi epsilon 0 r squared. And this is exactly what you would expect for a point charge. So your result is correct regardless of you using any Coulomb's law. So this is the electric field in the region where r is less than a, meaning you're in the region of the configuration where you are living inside the inner spherical conductor, okay, which is basically hollow, just at the point, just a point charge at the center. All right. So the hollow portion was not part of the conductor. Now the next interesting region is the one that is in between the two thick walls of the inner conductor. So the radius of your Gaussian surface, if I call that r, let's draw that r now. If this is now my r, then r is greater than a but less than b. So I can write r is greater than a, however r is less than b. Okay, so that is the radius of my chosen Gaussian surface. Now the Gaussian surface is different from the first part's Gaussian surface. All right, so this is inside the conductor itself because it's between the two thick walls of the conductor. So you have to be a little bit clever about applying Gauss's law. All right, so let's start by just writing down the formula for Gauss's law. So we are in the region of the looking for the electric field EdA, integral cosine of the angle between E and dA, which is theta, equal Q enclosed over epsilon 0. Now I know for a fact that electric field is 0 inside a conductor. So that you know the answer automatically. Electric field must be 0 inside a conductor because charges on a conductor resides on the surface. And also the inner shell is neutral. So that means either way, then even if you consider the charge to be something else, you cannot say that charge is anything else but 0 because inside of a conductor the electric field must be 0. So how does the electric field become 0? If the q enclosed is 0, how is the q enclosed 0? Well, you have point charge q at the middle, that is inside your hollow portion. Then this point charge q is going to attract all of the electrons that are free to move about in the conductor in the inner shell to as close as possible to itself as possible. That's the attractive Coulomb force, remember? So the inner walls become highly negative because all of the electrons from all parts of the conductor basically rush towards that positive point charge. So the inner wall, the surface near the inner wall of the conductor will become negative. So how much negative do you think it's going to be? Well, of course, it's going to be exactly minus little q because only the amount of electrons needed that is equal to the positive charge q at the center will come close to the positive charge q. So the inner wall is then the total charge of that inner wall is then exactly negative of whatever charge, whatever the magnitude of the point charge is. So we can write this q enclosed in our case is plus little q for the positive point charge in the middle added to all of the electron charges that have come near it, which is exactly minus little q. So if you add this, of course the answer is 0. Q enclosed is then 0. So we have an explanation for why the electric field must be 0. Because the Q enclosed is 0 in this region. And it must be true electric field is 0 because conductors will never have charges living inside them in electrostatic condition. Alright, so the electric field in the region where your Gaussian sphere radius is greater than your inner radius of the sphere, A, but less than the outer radius, B. So let's take a moment to think about what's going on. Well, the electrons are being drawn near to the positive point charge in the middle. So, of course, they leave a net positive charge on the outermost surface of the outer shell. Oh, sorry, of the inner shell, right? So, if the inner surface of the inner shell becomes negative Q, the outer surface of the inner shell becomes positive Q. All right, because the overall shell must be neutral. So then the next region of interest for us would be the Gaussian sphere that is living inside the outermost shell but outside the innermost shell. So the radius r for my new Gaussian surface would be greater than b but less than c. Okay, because it's inside the outer conductor but outside the two thick walls of the inner conductor. All right. So now let's apply again Gauss's law. But to apply Gauss's law, we can we know what the setup is going to be. You need to be able to calculate what the EQ enclosed is. What is the total charge that is inside my newly defined Gaussian surface, right? And also, it's important to remember that this is a region that is in vacuum, that is not part of the conductor. So it's outside of the inner conductor and inside of the outer conductor. But remember that both of the conductors are hollow, so in between they have no conducting material. So in this case, it's we are living in vacuum, right? So again, we start by writing down Gauss's law. And now, what is Q enclosed? Well, you have positive Q charge in the middle, that is the point charge. The inner wall of the inner shell is negative Q. The outer wall of the inner shell is positive Q, right? So if I were to write down what the Q enclosed is, take a moment to think about what Q enclosed would be. It's the total charge inside my newly defined Gaussian surface with radius greater than B but less than C, right? So what is the total charge? Pause the video and think about it. All right. Now let me write it down. Let me give you the answer and see and try to see if your answer or if your thought process was right. So we have plus Q in the middle, the point charge. Then we move on to the inner wall of the inner shell, that is negative Q. And then we move on to the outer wall of the inner shell, that is the last surface that is inside my newly defined Gaussian surface, and that charge must be plus Q as well, right? So you have cancellation of plus Q with 1 minus Q. So leaving behind a net charge of plus Q. That is divided by epsilon 0. So the electric field would then be, of course, theta would be 0 because E and dA are parallel in case of positive charge. So overall charge is positive. So the electric field and area vector would be parallel. So the electric field would be very similar to the one we calculate, exactly the same actually, for the one we calculated before for part number one. However, it's good to note that the radius is not the same. Here we are enclosing a bigger Gaussian sphere. However, it doesn't matter because the charge in both cases would be exactly the same. All right, so the radius would be different, so the electric field will be a little bit electric field, of course, is proportional to 1 over r squared. So the electric field in this region would be weaker than the electric field that is in the inside of the two thick walls because of that point charge plus q that we calculated in part 1. So this is the electric field in the region where r is greater than b but less than c. So we have one last region of interest, that is this region right here, that is completely outside this all of the spherical configuration. So the radius of this Gaussian surface R is bigger than C. It's bigger than the outermost conductor. All right, so the region you're looking at is the region that is completely outside all of your conducting spheres. All right, so this is my region of interest. Now let's apply Gauss's law and remember that outside there is no conductor anymore. Completely outside, of course, it is a region of vacuum. All right. Okay. So now try applying Gauss's law for yourself. Take some time. Let's pause the video if you want for 1 or 2 minutes. But uh, let me just start Gauss's law. And the first step is always to just write down the Gauss's law equation. All right. So in the question, it is given that the outermost conductor has overall charge plus capital Q. So my first step is going to be, what is Q enclosed? What is the charge that is inside my defined Gaussian surface? So of course, we have the outermost conductor inside my new Gaussian sphere. So the first charge I consider is plus capital Q. Then we have everything else that is also inside. We have the charge on the outer layer of the inner shell plus Q, the inner layer of the inner shell minus Q, and also the charge that is completely inside at the center, that is plus little q, that is due to the point charge. So that is the total charge enclosed. You add them up, one of the q's cancels out the minus q's, so we can easily cancel one of them out. So the overall charge that is inside my Gaussian surface is capital Q plus little q. All right. So it's basically the charge that is on the outermost sphere and the charge right at the middle, the point charge right in the middle. Everything else is neutral. That is how it should be, right? The inner shell was neutral. So we can just write down Gauss's law at this point because we have done the Gauss's law application so many times now. So the total charge is Q plus capital Q divided by 4 pi epsilon 0 r square would be your electric field. The r in this region is greater than C. All right. So this is how you apply Gauss's law, and it's good to practice similar problems. Now the next step would be to think about, okay, what is going to be the case? What is going to be the electric field if I now consider both shells to be thick? Then consider only the outermost shell to be thick. So thickness means it has two radius, one inner radius and one outer radius. And then do variations of this problem to get a hang of using Gauss's law.